we will again continue our journey related to the studying root systems. So just we will start by recalling what we did in the lecture 1. Recall. We started with a reflection, which is a basic linear operator, which
Sachin,
fixes.
एक second, sorry. So please turn your laptop camera a bit because there is some glare coming from the window. Yeah, so you are completely in light. Just turn it a little bit.
Is it fine?
Yeah.
It is good now?
This is good now. Yeah, thanks.
So reflection, which fixes an hyperplane and maps every vector orthogonal to the hyperplane to its negative. And then we prove that if you have a hyperplane and suppose some conditions are given with respect to some set which spans this, this is nothing but the unique reflection actually. Okay. Then we defined root systems, which is a main object of study, or a space, vector space over a finite dimensional vector space over a field R. And then we associated actually a very nice group with those root system, this thing, so which preserve the root system called as Weyl group. What eventually, suppose you have a vector space over R, it always enjoys having very nice inner product. So we have an inner product, so which we have bilinear form, which is in fact it is a positive definite and W invariant, in fact AR invariant if you think. And so then we will define the direct sum of root systems, and which pave way for us to define irreducible root system. Okay, and so what we were yesterday at the point that this when you have a W action on this irreducible root system, this action is irreducible. In fact, this is actually if and only if statement. I will begin with recalling what we have where we were. So here was the statement, here was the theorem, which says that if W phi is V phi is an irreducible root system, then W acts irreducibly on V, and the converse is also true. So we would like to show that suppose phi is an irreducible root system, then V is an irreducible representation of the Weyl group W of phi, or simply I'll write W. Okay, fine. So in case assume contrary, V is not irreducible. Okay, V is not irreducible. Then as W is finite group and V is finite dimensional, over R we have V is equal to V1 direct sum V2, where V1 and V2 are non-zero W representations. Okay. Yeah. Now we will be done if we show that phi is equal to phi1 direct sum phi2, where phi1 is phi intersection V1 and phi2 is just nothing but phi intersection V2. Okay. So that will partition your things, and these are all root system in itself. And why they are root system? Because they are invariant under W and satisfies other properties. Okay. So how we will proceed? So far, any questions? This is just we are beginning from where we have left yesterday. So let alpha belongs to R. And so we have, and let V belongs to V1. Consider S alpha of V. By the definition, what we have is, this is just nothing but 2 alpha V, alpha alpha of alpha. Now, as V1 is a representation of W, where does S alpha V belongs? Anybody from the audience?
V1, because V1 is a sub-representation.
Yeah, absolutely, Sanu. So this is because it is W invariant, so it belongs to V1. Okay. Yeah. But if alpha does not belongs to V1, that would what would that imply? That would imply that alpha of V is equal to 0. More precisely, alpha check of V is equal to 0. Right? Similarly, so in case if alpha does not belongs to V1, that implies that V1 is contained in H of alpha, which is these things are such a set of all vector V dash belongs to V such that alpha of V is equal to 0. V dash is equal to 0. Okay. So what does this imply? This is actually one of the exercises taken by Ritesh. So this implies that either alpha belongs to suppose these things, suppose alpha does not belongs to V1, that would imply that so this is V1 is contained in H alpha. But you see that V1 is contained in H alpha direct sum R alpha, because that is your whole V. Okay. So eventually, similarly, this we see that any alpha belongs to R, that would implies either alpha belongs to V1 or alpha belongs to V2. Similar argument you can play by taking V belongs to V2. Okay, and that's it. And so you manage to partition phi into the disjoint union, into the direct sum of phi1 and phi2. These are the, I should say disjoint union, as direct sum doesn't make sense. So this is, yeah, and so, yeah. Okay, and they are root system because S alpha keeps, the W keeps phi1 invariant and W keeps phi2 invariant. And so the converse, I leave it to you, exercise, and follow similarly. So try to do it. Yeah, here we have used Mushke's theorem, a very famous theorem, which says that every finite dimensional representation of a G, which does not divide, where the characteristics of the field of the corresponding vector space, which is does not divide order of G, then you can actually, your V is completely reducible. In the sense that V you can write down in terms of its simple modules, actually, in terms of this direct sum of some simple modules. Okay. So fine. So we are here. And this is very useful information. This is very useful information as the interplay between the geometry of how the Weyl group acts on the root system and how does it help us to reveal the information about V is very important. Okay. So we'll continue. Now we focus on.
Can I ask a question?
Yeah.
So, is there any group theoretic characterization of the Weyl groups of root systems?
Of course, they are generated by the reflections. They are nothing but a type of Coxeter groups, actually. Okay. Yeah.
Okay.
And,
so I don't know what Coxeter groups are. So that's why.
It are some groups which are defined by some integers defining relations Mijs. But maybe in the next lecture I will mention something about that, actually. Huh?
Okay. Fine.
So yeah. So these groups are very well studied, and these are very classical groups, actually. So yeah. So we are where we are. So now let us now analyze. So these root systems, see, we cannot have an arbitrary things because you see they are invariant under the Weyl group action. So that forces this constraint is extremely restrictive. So what you have, so suppose, so as we are working, space, suppose you have two vectors, alpha, beta. Does one know what is the inner product alpha, beta in terms of their norms? What is the expression? I mean, I shouldn't write here as orthogonal, just like what you would write this inner product as? Some of you?
Norm B times cos theta.
Norm alpha, norm beta, cos theta, isn't it? That's how you write it. Yeah. This is the usual Euclidean thing. Now, let us define a term n alpha beta, which is nothing but twice of alpha beta, beta beta. Okay, this is my definition. Now, using this above identity here, and suppose you, so this is an integer. Remember what it is? What it is? You know, anybody? This is in terms of check. What it is?
Beta check of alpha.
Very good. It is a beta check of alpha. Okay, this is the thing. Yeah. Similarly, n beta alpha is nothing but alpha check of beta. Okay, so this is 2 alpha beta alpha alpha. Fine. Now, but as you see that, but what is the more thing actually? This is just nothing but an integer, right? This is what our root system for these things. Suppose alpha and beta belongs to phi. I should mention here. This is an important thing. Then these both are coming from integers, and this is very strong condition. Okay. Now suppose we multiply n alpha beta with n beta alpha. Can one tell me what is this product is equal to? This is just nothing but twice norm of alpha, norm of beta divided by norm of beta square cos theta. Again, twice of norm of alpha, norm of beta, and this is norm of alpha square cos theta. So this is equal to, so we'll have, this is just nothing but 4 cos square theta, which belongs to Z. Okay. Now, can one tell me what are the possible values this product can take? Yeah.
4,
Yes,
0,
very good. 4,
0,
0,
Could be 1,
1,
2,
2.
3 also.
3 also.
Huh? Sorry,
3.
3 also. Why? Because your cos theta is always less than 1. Okay, its modulus is always less than 1, and that's what you will have, right? And that's it. You note that because see, it's a cos square theta, so it is again it will be a positive thing. Okay, so yeah, we are in very nice shape now. That we are there, and so both will have n alpha and n beta will have same sign. Okay, either n alpha, if n alpha is negative, then n beta is negative. That is obvious because you have alpha beta is equal to beta alpha, because there it is a symmetric form. And so we can actually work on and find a nice table here, and so which is very important, and you must help me in this thing. With respect to the, these are called as a configuration of roots. So what you believe, what are the constraint with respect to the root between, angle between the thetas, actually angle between the simple roots, not simple root, sorry, simple is, it will come the simple root, angle between the two roots. So theta. So the first is, suppose you have a 0, then it forces this thing is equal to 0. Then what do you expect? Norm beta by norm alpha. Yeah. Anybody? It can be arbitrary anything actually. Your norm alpha could be these things. So it is undefined here. You will never able to come to know. And as they are orthogonal, we expect their the cos theta angle should be pi by 2. Okay. The second thing is 1. Both are having equal length here. What do you expect of their angle now here? Please do the calculation. So what does that imply? It implies that n alpha beta is equal to 1. That implies that 4 cos square theta is equal to 1. And so cos square theta is equal to 1 by 4. Yeah? Tell me what should be the cos theta? It should be
45 theta.
plus minus half actually. But whether it will be plus half or minus half, tell me here. Can anybody answer this question?
Plus.
Reason.
Because of n alpha beta?
No, n alpha beta. But Aditya, why it is not actually the 2 by 3 angle actually? Okay, I mean, so of course, why it is minus 1/2? Because n alpha beta, and you see that the angle must be acute one because their inner product is greater than 0. Okay. So if the angle is obtuse, their inner product is less than 0, less than equal to 0, and if angle is acute, this thing. So what will be the angle? For what? what acute angle of cos? Its value is 1/2.
Pi by 4.
Huh? Yes, Tanu?
It's pi by 4, sir.
Pi by?
4.
Pi by 3, right? Am I doing some
Oh,
mistake?
yes. I'm root 2. I'm just no, sorry, sir. Pi by 3.
Okay, no issue. Similarly, for now, you take other these things -1, -1, and again, so here you will have these things. Now here you should tell what is that. Here you have -1/2, and it should be.
So 2 pi by 3.
Angle? Huh?
2 pi by 3.
Very good. It is just nothing but pi minus pi by 3, which is nothing but 2 pi by 3. Okay. So this is very simple, basic algebra I am doing. Nothing complicated. In case if you have doubt, don't hesitate to ask, or you ask your friends. Okay. So I'm not doing any complicated thing. So now, so you will have 1, 2, and their ratio would be, if you calculate, it will be √2. And here angle again, you should have a cos table with you. What will be the angle? Anybody?
So would it be pi by 4?
Pi by 4.
Pi by 4. Okay. Take the negatives. What will be here? What is that? 3 pi by 4. Okay. Now again 1, 3. You will have √3. This will be pi by 6. -1, -3. This is √3. And this is pi minus pi by 6, which is 5 pi by 6. And these remaining are the uninteresting cases. I will ask you why they are uninteresting. So this is 2, 2, 1, 0. Two minus 2 minus 2. But it is the same line. It is like these things. So you have a vector, it's the same, its angle is 0 with itself, has a length 2, or it is a negative of that vector actually. So these things will not be very interesting, these two things. But what will be, these are definitely except the first one is definitely the interesting one. Okay, and we will look at that. So please, if you have any question related to so far what we have covered, just I'll pause for 10 seconds to have anything, any doubts? Okay, fine. Yeah, so we have, and so this is very informative as one of the application of about, well, there are many applications, but I would just like to mention one application. So you will see that if alpha beta belongs to phi, and if n alpha beta is greater than 0, then alpha minus beta belongs to phi. B, if alpha beta belongs to phi, and if n alpha beta is less than 0, then alpha plus beta belongs to phi. A very important result. So it is always important to know when the combinations of roots is you are getting as a root actually. Okay, so it's not always easy, but with this table we will see that this result is evident. Okay, so the proof. So what do you have? Like anybody from the table? The proof follows from table. Can one help me in this proof? Okay. So you see that in this table, suppose n alpha beta is positive. Okay. So what we will see, you all observe that at least one n alpha beta or n beta alpha, you will have one actually. Okay. Isn't it? You see, these are not, I'm not covering all the cases, as here you will have 2 and 1 also. This case also will be there. But I will see that as this is a very similar to that thing, just to say the mirror image of those things. So I'm not considering that case. In technically, I should mention at the first place 2 and 1 also. So you will see that if n alpha beta is greater than 0, that would imply that either n alpha beta is equal to 1 or n beta alpha is equal to 1. Assuming n alpha beta is equal to 1, we will see that S beta of alpha. What is S beta of alpha? In terms of n alpha beta, can you tell me? So this is just nothing but alpha minus 2 alpha beta by beta beta into beta. So this is just nothing but alpha minus n alpha beta of beta. So this would imply that this is just nothing but 1. So this is nothing but alpha minus beta. But S beta preserves the root. So that's why this belongs to phi. And I leave for alpha beta negative case for you. Okay. Yeah. So we have very nice corollary of whatever table we have. But let us.
Sir, I have a question.
Please.
Sir, are we assuming that alpha and beta are distinct? Otherwise, we'll just get 0.
Of course, we are assuming alpha and beta distinct. Okay, I should mention that actually. Okay. Yeah. Otherwise,
okay.
You see, we are in trouble, right? Rightly pointed by you, right? Because 0 never belongs to phi. Yeah. Okay. Is that fine?
Yes, sir. Thank you.
Okay. Fine. Okay. So let us continue our journey. Now, concentrate. So we'll worry about the rank 2 root system. Okay. So now let me start with my first root alpha 1, 1, 0. Okay. And I will take another angle with respect to the another root as a pi by 4, 45 degree with respect to that angle. So what should be the length of that alpha 2? Assuming that alpha 2 has a bigger length than alpha 1, what should be its length? Just look at the table and tell me. It should be. So what is the unit vector? The 45 degree angle here. This is just nothing but cos pi by 4 sin pi by 4. But this is a unit vector. We want such that their ratio of alpha 2 by alpha 1 should be root 2, right? Isn't it?
Root 2.
Sorry?
Root 2.
Yeah, so your voice is not very clear. Can you, who is that? So this vector should
He
be
said
root
root
2
2.
multiple of those things. So what are these vector? This is just nothing but root 3 by 2, 1 by 2. Okay. Yeah. So this is now again a third, again root these things. Again, I will go with 45 degree. And what should be its length? This is my alpha 3. It turned out that you cannot have its length root 2 times of these things. Okay. It should be you will come to know that there are at most 2 root lengths. Okay. By using the action of irreducibility on the root system. Okay. Irreducible root system. Okay. So this is a 90 degree angle. These things again you move it by 45 degree. This is your alpha 4. You will have again 45 degree here. It's negative of those things. Negative of this vector also. And this is the thing. This is the last vector. Okay. And that's how you complete your square. Okay. This is alpha 1, alpha 3, alpha 5, alpha 6, alpha 7, alpha 8. Okay. Yeah. This is indeed a root system. What is the name of this root system? Anybody from the Lie algebra background? Yeah. This is B2. Okay. This is root system. This is just from the diagram and knowing that there are only 2 root lengths. Okay. That's how you get it. Yeah.
Sir, I had a question.
Yeah,
the last
please.
theorem we proved and we made a table that is true for any arbitrary root system, and we're just applying it to this one.
Yes. Yes.
All right. Okay, sir.
Okay. Yeah. If you are not very happy with these things, let us have another root system, which is, let us again start with your unit vector alpha 1. Okay. And your angle is pi by 3 now, pi by 6 now. So what should be its length? What should be its length, Daksh?
So it would be pi by cos pi by 3 is 1 by half times the
Cos pi by 6 and
yes.
sin pi by 6. And you have to multiply by root 3 actually, right?
Yes,
okay.
Yes, sir.
So this will be some vector here. Okay. Now alpha 3. This is alpha 1, alpha 2. This is your 30 degree angle, pi by 6. Now choose pi by, so again pi by 6. So this is pi by 3. What should be its length? Alpha 3. Anybody?
Root 2.
What is the alpha 1 and alpha 2's alpha 3's thing, root length? What should be? What should be their ratio? Suppose angle between the 2 roots is pi by 6. Okay. It forces that. What does it forces? Check the table. Sorry, if the angle between two roots is pi by 3, then what it forces you?
Ratio should be 1.
1, 1. Ratio
It
should be 1.
1. So it should be unit length actually. So the play the game same now for alpha 4. Alpha 4 has angle between alpha 2 has its length is there should be same. So it is a root 3, these things. So again, this will be the yeah, alpha 2, alpha 3, alpha 4, alpha 5, alpha 6, alpha 7, alpha 8, alpha 9, alpha 10, alpha 11, and alpha 12. Okay, this is a beautiful root system, rank 2 root system. Indeed, it is a root system, and it is named as G2. Okay, and so considering these A1 cross A1, A2, B2, G2, these are all the rank 2 root system. These exhaust all those things. Okay. In case if you have doubt, don't hesitate. Please ask.
Sir, I just have a single question. Yeah, it seems like it can seem like a stupid question, but let's say we are doing this rank 2 root system and
Right.
we are doing it from the table, right? So alpha 1 and alpha 2, these are two distinct root system. These are two distinct roots, and the angle is between them is pi by 6. So you are drawing.
Correct.
As soon as you are drawing alpha 3, that means you do know the existence of a third root in the root system.
Correct.
So
correct,
how
correct.
from the table it follows that there exists a third root? I do believe once you have alpha 1, alpha 2, you have minus alpha 1 and minus alpha 2. So you get 4 roots. But then how are you ensuring that there exists another root alpha 3, which will have an pi by 6 angle with alpha?
It is, I'm cheating a little bit actually here, just to give these things. It follows from the little bit more subtlety about the simple roots, and which we will come to know actually. Okay, just for it is showing the students right now a priori, yes, we don't know why there exists a root actually, this alpha 3. Okay, as far as, but you will see that alpha 3 is alpha 1 and alpha 6 actually. Yeah, the angle between alpha 1 and alpha 6, this is actually a 150 degree, right? Isn't it? Yeah. And they are, like we will come to know, as you know, Snehashis very well, the simple roots are there actually, right? These are the simple roots actually. Yeah? And these in between roots, they comes as their linear combinations actually. Okay. And you will show that, see, eventually you will show that these are the, I mean, they come as the roots actually. Okay. For alpha 1 and alpha 6, you know that alpha 1 plus alpha 6 is a root. Okay.
Yes.
Can you figure it out? Which root is that? Here.
Yeah.
From here.
I mean, as a vector, it should be actually in the middle of alpha 1 and alpha 6. So it seems like it's going to be alpha 3.
Right. So that's it. I answered your question in the other way actually, right? Isn't it?
Yeah.
So
Yes.
In the table, you would come to know that, see, even though, but you may caught me up with alpha 4 now. Okay. That is the thing. Yeah. I mean, alpha 3, just by fluke, actually, I would be able to tell you that alpha 1 minus alpha 6 actually, or alpha 1 plus alpha 6 is there actually, right? Okay.
Yes.
But to get all the roots actually, we need to utilize maximum use of the Weyl groups actually. Okay. And a little bit representation theory. Yeah. Okay. In fact, what we are saying that it is a root system here, but proving that there exists a Lie algebra with the following root system requires a more subtle stuff. Okay. Which I don't think we will be able to cover in these three set of lectures actually. Yeah. Okay.
Okay.
So yeah, thank you for your question, but it is an important one. And like, yeah, it should come to your mind that why it is the thing. But you see, the many of all these things. So suppose you have the angle, which is the smallest angle is nothing but pi by 6. So it is a consistent with that thing. Okay. So you will have the next angle thing also there. Okay. So that is a one kind of these things an assumption, but we will later prove that this is actually a reality. Hopefully we will say something about that. Okay. So let us proceed. But in case I think that you should not get scared of what are the root system. This is actually, you come to know now that these are 30-degree apart vectors, and with the nice thing, nice norm and all these things, you know these things. Okay. So let us continue now. We, as Snehashish asked me that we should do something more, so I will go to the more theoretical approach now, and studying like the interdisplay between the geometry and algebra. So here is the thing which we will say: chambers, bases, base, and or it is also Bourbaki says at basis, and the Weyl group W. We have already introduced these things, and we will see their interplay. So note that a definition actually. So we are assuming that phi, if alpha belongs to phi, R alpha intersection phi is nothing but alpha minus alpha. If you assume such a condition on the root system, it is always called as a reduced root system. Okay, so it is called as reduced root system, and we are always working with okay. Yeah. Now consider the space, consider the so let us start with V phi. V is finite dimensional vector space, and phi is system. Okay, let H be the set of all hyperplanes. H alpha, which is nothing but kernel of alpha check. Alpha belongs to R. Okay. Observe that the Weyl group preserves H alpha. Alpha belongs to R. Why? Anybody? Like what way is the, I'm saying that suppose V belongs to H alpha. I claim that H W of V belongs to H of W alpha. Is it obvious to all? In other words, W of H alpha is equal to H of W alpha. Why does it follow? Why does it follow? So V belongs to H alpha means what? V of alpha is equal to 0. But that implies that, so what do you expect? WV of alpha. But as this form is W invariant, this is just nothing but V
W inverse alpha.
just to hold on. So V alpha is 0. That implies that W alpha is 0. Is it like, are you fine with that? Because your form is W invariant, right? Okay. So that would imply that what about converse? Need to prove that but this is obvious, right? I leave it as an exercise. Do these things. Okay. Yeah. So I request Ritesh to consider this as an exercise. It is a one-line proof, as I'm sure you. I will be there, but just to think. So W indeed maps a hyperplane to the hyperplanes. Okay. And consider the space defined as V regular as V minus union of all H alphas. Alpha belongs to R. Okay. This is the space. As this union of H alphas is preserved by W, this complement of union of H alpha. So V regular, W maps, V regular, the space is preserved by the W as each of these things. And W is, remember that it is a linear isomorphism. Never forget that it is a 1-1 onto a very nice map. Okay. Now, to make this thing geometrically clear a bit, I will start with this A2 system. So what is A2 system you have? This is alpha 1. The another root has obtuse angle of 120 degree. This is your another root, and their addition is this another thing. So you have alpha 2, alpha 3, alpha 4, alpha 5, alpha 6. Okay. Yeah. Now I just need to consider their hyperplanes. Okay. So this is hyperplane which is perpendicular to alpha 1. Fine. And this is plane curve perpendicular to alpha 2, and we are remaining with one more. Okay. And so this is, so I will just have another. Yeah. So these are the hyperplanes. Okay. Yeah. Now the what we say here is that chambers, what are the chambers? Chambers the chambers are defined as connected components of V regular. Okay. Yeah. So they are the connected components of the V regular. So here, what are the chambers? So here chambers are I'm numbering just arbitrarily, so don't worry about 3, 4, 5. Okay, so these are called as a chamber. Just to give you the picture, this is we are working in SL3, and these are the chambers. Okay, what are these? There are how many chambers? There are 6 chambers. Okay, they are connected components of the V regular. Okay, fine.
I have a question.
Uh-huh.
You said that we'll be working with the reduced root systems. So what is the connection between a non-reduced root system and a reduced root system? I mean, in what?
Very good question. Actually, unfortunately, Professor Shraddha couldn't complete that thing. See, what happens is that we are mainly working with the semi-simple Lie algebra. Okay, in that semi-simple Lie algebra, you will have a root system which turns out to be the reduced one. In the semi-simple Lie algebra, there are also roots actually. It turns out that if alpha is root, 2 alpha is not a root actually. Okay. So that's why we are mainly concentrating on these things. But you are absolutely right that there exist non-reduced root systems, and they are also studied well in the literature actually. Okay. So I hope it answers your question.
Yeah, I actually thought that the non-reduced root systems could be expressed in some way in the form of reduced root systems. That's why we are studying this, but that is not the case.
That is not the case actually.
Okay.
Huh? That is not the case. As best of my knowledge, that is not the case actually. Yeah. So, yeah. So here we have defined chambers. Yeah. Now, what is these things? Now, this partition in terms of those things, regular and these things, will make me define a positive and negative roots on the real roots actually. What are the positive roots and negative roots? So here is a very crucial thing. What is that? What is positive and negative root actually? Okay. Now, first of all, question. Let X belongs to C, where C is one of the chambers of V. Fine. What can you say about X alpha, where alpha belongs to phi? Anybody? This is a very basic but important question. suppose it lies here. Your x is here. Okay. What about this alpha 1? So this is alpha 1, alpha 2, alpha 3 and all these things. What is inner product with these alpha i's? What can you say? None of you can. It's a non-zero. Yeah, it's non-zero. So this is non-zero. Why? Because x doesn't lie on any of hyperplanes. Yeah, it's very simple, as that. And so what we do is we define r plus of x as alpha belongs to phi, alpha x greater than 0, and r minus of x alpha belongs to phi. And this indeed partitions your R. Can someone tell actually what is the relation between R plus of x and R minus of x? Yeah.
If you take the negative of all the elements of R plus,
Your voice
would
is
that
very low. Can you increase your voice?
if we take the negative of all the elements of R plus, will that give us R minus?
Obviously, because we will be able to show that if alpha belongs to R plus of x, then minus of that is belongs to R minus of x. Similarly, vice versa. So they are actually, so what we have is R plus of x is just nothing but the negative of R minus of x. Okay. So that actually kind of partitions equally in half of your root system. Okay. But how much this partition is dependent on your x, which belongs to the Weyl chamber, Okay. So here is the following lemma, which says that suppose if x and y belongs to V regular, then R plus of x is equal to R plus of y, if and only if complete the string. If x and y belongs to the V regular, then Rx is equal to Ry, means that the positive roots related to the partition we have defined with respect to xy, they are same if and only if both x and y belongs to the same chamber C. Okay, this is an important thing. So suppose what does it tells that your this partition is independent of the point if you have taken from the same chamber. In the same chamber, of course, there are uncountably many points. But you take any point, and if it is the same chamber, then this partition of your R with respect to R plus of x and R plus of R minus of y is R minus of x is will be remain same regardless of x actually. Okay. So let us start. So suppose x and y lie in same chamber C, need to prove that R plus of x is equal to R plus of y. So as usual, suppose contrary. Yeah. So what will happen? Can one tell me what is the contrary? What will happen? I mean, of course, contrary means this is, yeah. So this will force us that there exists alpha belongs to R plus such that R plus of x such that alpha of x is greater than 0 of this, and okay, this is the condition it should follow. Otherwise, they both will be equal, right? So what you see here is, this is, let us say, this is a hyperplane alpha. Your x is here above and y is below. Now, is it a contradiction? Someone from the audience? Does it give a contradiction? Note that x and y are from the same chamber. Looking at the picture, what it is showing you? It is separated by the hyperplane, isn't it? Can it be in the same connected component as contradicts the hypothesis that x and y belongs to the same chamber C. Okay. And for the converse, I leave you an exercise, but the argument is similar one. Okay. So please take these exercises seriously. In case if you don't able to do that, with at most with honest trying also, so you can ask us in the tutorials. Okay. So now we will proceed. Okay. So we will proceed. So what we have is that given any member of the same chamber G, it will have same Rx and same R minus Y. So now let us fix a chamber C. So let us fix a chamber C. Now we'll define, and so what we'll have is R is nothing but R plus, R minus. Okay. This C is fixed here. C is, this is R plus of C or R plus R minus of C. By our last result says that R plus of C makes this definition true because R plus of X is equal to R plus of Y for any element of C. Okay. So that makes this definition clear. I mean, it's well defined. Now, definition, a root beta in R plus is said to be decomposable it's said to be decomposable if alpha beta is equal to beta 1 plus beta 2, where okay, yeah, so this is when you say beta 1 plus beta 2, as in case of A2, root system A2, Can one tell me, suppose one take which hyperplane? So I just want to take some chamber. So again, let me take the chamber number 1 here. With respect to that thing, we will have a partition. So with respect to the chamber 1, can one tell me what are the positive roots here? So I want all of alphas which are with respect to the x, their inner product is greater than 0. You will see that this alpha 1, when you will have an inner product greater than 0, if their angle is acute angles between them. So you will see that this member and this member are on R plus. They lies in R plus actually. And this member, and this member, they are in R minus. Among these 3 roots, please answer which root is decomposable among these 3 roots. Yeah?
Alpha 2.
Alpha 2. Very good. Very good. So alpha 2 is because it is a alpha 1 plus alpha 3 is nothing but alpha 2. Okay. And you will see that alpha, these thing, alpha 3, you cannot write a linear combination of these two. What is the reason? I will leave it to the reason, but you will never able to write alpha 3 in terms of the alpha 1, alpha 2. Okay. So note that the angle is obtuse here. Okay. So that is what explanation of a decomposable thing. And so it paves the way for us to define indecomposable root. A root beta belongs to R to be F is said to be if it is not okay. So if it is not decomposable, then it is indecomposable. Like in the previous example, alpha 1 and alpha 3 are the indecomposable roots. Okay, fine. Now we define base of C. This paves the face. So the base of the chamber C or root system, these things, or with respect to the chamber C, is defined by ta belongs to R plus of C, B is indecomposable. Okay, it's very important. So we are going towards the indecomposable roots, and they play pivotal they play pivotal role in the theory of Lie algebras and root system. Okay. Fine. Now, so here is the thing is that what is the importance of that? So this following proposition, it's best to tell you about what is the importance of these things. So P of C is indeed a basis of V. Okay, note that we have started with these things. And not only that, R plus is just nothing but you can write it is contained in the non-negative integral combinations of elements of B of C. These things may write actually Z combinations of element of B of C. Similarly, R minus this is extremely important. Okay. So what is that? That every root you will write not only arbitrary combinations, but non-negative combination, integral combinations of the BC, the base. So which is actually a very, very nice properties of the root system. How do you see that? The proof. First of all, let us try to prove that B of C is basis of your vector space V. Yeah. How do you see that? This, the part of basis will be clear. Will be clear from the assignments today, the tutorial sections. By Ritesh and me, that where here is the statement is that any set of vectors lying strictly on one side of hyperplane in Rn and forming pairwise obtuse angles must be linearly independent. Okay, fine. Now the question is, I have a question for you, is that why the elements of this base forms an obtuse angle? Can anybody reply? I mean, see, first of all, so alpha and beta belongs to C. What do we expect their inner product? Can anybody guess? Am I asking very difficult question? I mean, B of C. These are roots.
They are in such same chamber.
Huh? No. They are, what is a B of C? These are all the set of all roots actually. See, what is a B of C? These are all roots which are indecomposable. Okay. I hope you have not lost in the definitions. And suppose this is greater than 0. What do you expect? What does our last result says that? Huh?
Alpha plus beta is a root.
Sorry, alpha?
Alpha plus beta is a root.
Alpha plus beta or alpha minus beta?
Sorry, alpha minus beta.
So this is belongs to root. Okay. Then what does it imply? Either this will be a positive root or this will be a negative root. But what happens if it is a positive root? Can you complete? It means that alpha minus beta is some gamma belongs to R plus. But what would that imply?
If alpha beta from base, any root will be either non-negative or non-positive linear combination.
That is correct. But you see, that will imply that alpha is equal to beta gamma. So here beta is also belongs to R plus and gamma is belongs to R plus. That will contradict that alpha is
indecomposable.
Very good. That will contradict that alpha is indecomposable. Okay. But what if, okay, this argument works very well, but what if it belongs to R minus? Can one complete? Can you complete, Aisha?
Then it is some equals to some negative roots.
Gamma belongs to R minus.
Yeah, which means minus of some positive roots. So then again, it will say that alpha is my beta minus of that.
Alpha is equal to
beta minus of that gamma.
No, plus of gamma, no. Alpha minus beta is gamma, right?
Yes, sorry, beta plus gamma, yeah. Then again, we will say something about the 8 alpha is.
So here is the trick is that the same argument alpha minus gamma is equal to beta, but this is nothing but alpha plus minus gamma. What is minus gamma then?
Minus gamma is positive.
So that's it. And so I leave it as an exercise that try to prove that R plus of C is nothing but contained in this thing, and R minus of C okay, good. What I want to make some more noise about very extremely important property that so what we have come to know, suppose alpha and beta belongs to B of C, then it has n of alpha beta is less than equal to 0, and so let B of C is equal to alpha 1 alpha 2 alpha n, which is a dimension of V, because this is by the thing, this is actually a basis for V. Remember that W of phi is just nothing but S alpha. Alpha belongs to phi. But the claim is that it's spanned by those things. claim is that W of phi is just nothing but S alpha I, where alpha I belongs to BC. Okay, these are the simple roots. So these indecomposable root also called as a simple roots. Also called as a this is also called as a simple roots. Okay. And so this is very crucial. Your big group, which is generated by so many elements, more than elements, you just have to be understand that you have to have generators very less in numbers, and that simplifies your lot of calculation. Okay. So what is the property is that one of the key property is that here is the first thing. How do you prove such a thing? Your first thing is that suppose you have a simple root or indecomposable root and you have R plus that maps to, okay, so this set. So only positive root which S alpha I maps to its negative root is alpha I. Okay. And that is extremely important property. How do you see this thing? Okay. Now let beta belongs to R plus minus alpha I. So by the previous result, we can write beta is equal to summation Cj alpha j. Okay. As beta is not equal to, and all Cj's are belongs to z greater than 0. Okay. This is due to these things. Every positive root you can write down as the sum of indecomposable roots or simple roots. What, as our beta is not equal to alpha j, what can you say about the Cj's? Anybody particular comment on that?
For J other than
Huh?
I.
Sorry? Huh?
I was for J other than I. Some Cj should be non-zero.
Yeah, there exists Cj belongs to 1 to n such that j is not equal to I and Cj is strictly greater than 0. Right? Agreed? Yeah. Not only non-zero, because these are all greater than 0, because these are all positive Z linear combination. Okay. So Cj should be strictly greater than 0. Right? And so suppose you do S beta of S alpha I of beta, what will be it? So beta minus beta of twice of beta of alpha I of alpha I. Now, can one tell me what type of root is this? Whether it is a positive or negative? We will stop after this proposition. But what I want is this. So this is your summation Cj alpha j, j is equal to 1. This is a beta minus some star of alpha I. Whether it belongs to R plus or R minus.
Again R plus.
Why? Why the?
Actually,
Why?
one of Cj is positive, so R
Right.
might be.
One of Cj is positive. So all the combination, whatever it comes, actually S alpha beta, that should be positive, right? Because you cannot have mixed coefficients. Okay. And that is what the power of these simple roots. Okay. So that forces you that S alpha b is in R plus. Okay. And that's what the result. I will end with an exercise that suppose, try to prove these things. Suppose let beta belongs to this fixed these things, any bit of R plus, then there exists W belongs to W phi such that W of beta is equal to alpha I, where alpha I is a simple root, any simple root. Very important, and we will start our lecture tomorrow with these things.